behind us as well. Whoops. So we actually work with a number of international entities. The people that aren't listed here that I like to mention are NASA. So based on some of the work I'm presenting tonight, NASA actually reached out to us. They flew out to meet us when we were in the States and said, hey, can we sign a partnership agreement, please? We want to be involved with what you're doing. Sort of. They do this sort of stuff as well. They do it on a very different scale to us, and I'll talk a little bit more about that. But we are now working together with them. The people that I've listed here are the ones probably more of interest at the moment. And I won't go through them all individually, but we have members from the University of Queensland, so we still work very closely with those guys. We have people from the Paris Observatory, that's the IMCCE that you see there, and in particular, Jérémy Vabaillon. He's an astrophysicist of great note, and as Jonty keeps mentioning, the absolute world leader in his field. So it's been a privilege working with him and a lot of fun. We have Stefan Löhle from University of Stuttgart, obviously where I did my postdoc, so we're still working together, which is great. We had the Comenius University of Bratislava with us, so they also do a lot of the meteor work, and this really just exemplifies the international group of people we're working with. And going forward, we're actually looking at expanding that, so we have quite a few more European partners interested, and also a lot more Australians. So the Curtin University in particular is probably one worth mentioning that we're going to be working with. So capturing things at 12 kilometers per second. I have two missions that I want to talk about tonight. The first is Hayabusa 2, which was a spacecraft capsule re-entry. And the second is a Tau Hercules meteor shower. And I'm going to go through both of them. And a little bit contrary to what Jonty said, I actually don't object if you ask questions during the talk. So if there's something on a slide that I don't explain or that you have a question about, feel free to yell out at me, and that's fine as far as I'm concerned. Or we can save it for the questions later. So why are we even interested? And this is the first topic. You know, I've talked to, well, Jonty introduced the idea of business jets, and that's correct. We go up in a business jet to do these missions. So what are we doing? We get a business jet, we take some cameras, we go up and fly next to something, and we take measurements through the windows. Now, the next to something is quite a big statement. It has to be something very interesting, not just anything happening in the sky. So we look for very particular events because there's obviously a lot of cost associated with this as well. So we want to really make sure that we get the most out of it. So why are we interested? At 12 kilometers per second, as you can imagine, that's really fast. Really weird things happen. So physics falls apart, chemistry falls apart, and the heating that happens from the gas is really strange. So the gas in front of this capsule, and I'll talk about capsule, but it's the same for any of the other examples I give. Capsule's coming in at 12 kilometers per second, starts hitting the atmosphere. The gas starts getting denser and denser, and all the little particles in the gas start bouncing around off the capsule and hitting each other. And the temperature actually gets up to about 20,000 degrees. Now that's really hot. And if you've got something that wants to survive, you have to protect it. Now, our interest is really in understanding how hot these things get. So I mentioned the physics and the chemistry goes a bit weird. It goes so weird that even NASA, at their very best, can say plus or minus 50% on how much heating there will be. That's worldwide best understanding of the heating of these sort of events. So we really need to get as much information as we can to help improve these models. And when I say plus minus 50%, that really is the very best. They're usually more like 100%. So there's a lot of interest in how much they heat. When something comes in, it burns up and it breaks up. Those sort of temperatures, then you start getting high speeds and the pressures associated with that. So depending on what the object is, that can be good or bad. Now, when we've got a spacecraft capsule, we generally want the thing to survive. So we need it to survive the heating. We need it to come down and land very slowly and gently without breaking apart. And this is the first example, the Hayabusa 2 that I'll go through, and that was a Japanese mission. However, there's a lot of other things that can enter the Earth's atmosphere. Meteor showers is the other one I'll give an example of today. You've all seen shooting stars. That's essentially all a meteor is. A meteor shower is just a lot of them in one particular event. I'm definitely not an astrophysicist, so I can't give you all of the orbital mechanical details of meteor showers. Please see Jonty for details there. He's always happy to answer questions. But when we talk about meteor showers, we essentially have clouds of dust, and the Earth's orbit and the dust cloud, they intersect, and these little dust particles come into the Earth's atmosphere. And because they're going so fast, they burn up, and that's when you get a shooting star. Now, a regular shooting star can be as fast as 70 kilometers per second. Due to the orbital mechanics of it. So 12 kilometers per second is actually the very low end of a meteor. But the reason I use that number here is because the Tau Hercules meteor shower that I'm going to be showing measurements from, that was at about 12 kilometers per second. That was a very special event, and it was a very slow one. And that presented its own challenges. The other things we're interested in, re-entering the Earth's atmosphere, we have space debris. And this is very topical at the moment. A lot of you will have seen in the news that space debris can break up and it can burn up, but you can also get 3-meter large chunks landing in your backyard. Now, tends to only happen if you have a really, really big backyard. And I listened to a podcast yesterday. It took them half an hour to drive from the front gate to where the space debris actually was. It gives you an indication of the size of the backyard. But space debris is a really important topic going forward. There's a lot of objects in space at the moment, satellites, spacecraft, rocket components, and all of them are going to re-enter the Earth's atmosphere at some point. In fact, it's mandated. If you put something up there, it's supposed to come back down. The idea is that it burns up and does not come all the way down to the ground. However, that doesn't always happen. And in particular, there's also examples of particular launches where people don't really follow the regulations because you can't enforce them internationally. And so even larger components will land on the ground. So for us, the really interesting piece is you've got to imagine a satellite could be fairly large, somewhere from 5 meters from a regular satellite to say 120 meters for the International Space Station, which will have to come in. When that thing comes in, whatever it is, it's going to break up and the pieces are going to disperse in different directions and some bits will land. What we don't have is a really good understanding of how these breakups happen, where the pieces go, and what the ellipse, as we would call it, the area where the pieces might land. Like, we can never predict exactly where a piece will land, but we can have an area that we can predict it. And these are normally thousands of kilometers in size. So any information we can get to reduce the uncertainty on that and reduce the risk and improve our knowledge of where pieces of land is crucial. So measurements of that can only happen in real life. We cannot recreate something like a spacecraft re-entry in the lab. We can recreate elements of it to understand very specific elements of the fundamental physics, but recreating the whole thing can't be done. So if we want to get real measurements, we're going to go up and watch a real object. And so that's one of the future targets of our observations. And prior to coming to UniSQ, I actually did 2 airborne observations looking at space junk, and that's something we want to do going forward. And the final one I mentioned very briefly is hypersonic flight. You would have seen in news, space is happening a lot more in Australia, or worldwide and in Australia at the moment. Things are flying faster. Everyone loves the idea of flying from Sydney to London in 4 hours instead of the normal 30 hours. So they want to be able to fly fast. But these vehicles need to be tested. And once again, the only really reliable way of getting data during a test is actually to watch it happen. So if everything goes well, you get data off the vehicle itself. But when things go wrong, you tend to lose all of your data. So the only way to get information is actually to video it. And to do that, you've got to be up next to it, flying near it. So these are all the sort of airborne observations we're interested in. But firstly, we're going to focus, well, actually, a bit of history, I suppose. Forgot about this slide. Previous missions that have been done. I talk about these airborne observations. And when I talk about previous missions, I'm talking about airborne observations, so going up on a plane and measuring them. And this is the missions that are in public domain. Now, military have obviously done their own suite of measurements, but we don't know anything about it. So these are all the public missions that have ever been done. And you'll notice it's a very short list. So NASA has done 8 or 9 missions in the past. And I'll highlight in particular that Hayabusa 2, which is my next topic, is one of them. The other thing I'll highlight here is that the initials I've put there, FZ is myself, but DB is actually Professor David Buttsworth. So we work very closely on this together. I tend to lead the missions and he does a lot of the diagnostics work. But this just shows our heritage, even here at UniSQ, in the history of these airborne observations. You know, there hasn't been that many, and we've been involved with quite a few of them. And the particular highlight, and what makes me especially proud, is of course the non-NASA mission column there. There's only ever been 2, and we led both of them, which is super exciting. Right, so now we're getting to Hayabusa 2. This is the slide I thought I was at. So Hayabusa 2 was an asteroid sample return mission. So JAXA, which was the Japanese space agency, they sent a spacecraft up, flew out to an asteroid, it landed, it collected a little bit of dust, and then flew back to Earth. Sounds pretty straightforward. It was an 8-year mission. It traveled over 5 billion kilometers in that time, and that's a really long distance. To plan a mission like that, to construct a spacecraft, to get everything to work and have it come back and land successfully was an amazing feat. So a lot of kudos to them. And this is the second time they've done it. So Hayabusa 1 actually happened in 2010. Hayabusa 2, 2020, and it landed in South Australia, like Hayabusa 1 as well. And this is where our interest really comes into it, because David and myself heard about it and we started reaching out to different parties and saying, hey, this thing's landing in Australia, we want to be up there measuring it. You know, this is our research interest and it's a lot of fun flying in planes. So we want to do that again. So we started reaching out and saying, hey, we want to be involved. What can we do? How can we get airborne? There's so much exciting science. It's an exciting mission. Let's do this. And we tried that for a long time and it didn't work out. So that was very disappointing for us. It was a long story, but in the end, about 3 months before the re-entry, we got told we can't be involved with any observations. I mentioned with any observations because NASA had 2 planes in the air. So JAXA, Japanese Space Agency, had actually contracted NASA to put 2 planes in the air to measure a re-entry over Australian soil, which they did, and we weren't allowed to be involved, which we were very disappointed about. Now, I mentioned Rocket Technologies International before, or a company that we work with, and the CEO there is a friend of ours now, and he gets very disappointed when David and myself get told we can't do anything. And we were just talking generally about this and told him that, you know, we can't be a part of the mission and we're very disappointed. And he said, well, if I give you a plane, will you go and do it? Well, yeah, I mean, is that an option? And he's like, well, I don't know yet, but just let's pretend it will be. So start thinking about it. And so that's sort of how this journey started. In the end, 8 days before the mission, he said, okay, we're doing this. Go, plan your mission, build your instruments, put it all together and go fly the mission. Now, 8 days to plan a mission where you've got to go fly an aircraft next to a spacecraft which is re-entering at 12 kilometers per second in an area in South Australia when you don't know exactly where it is, you don't know where to look exactly, you don't have any instruments, you've never seen the aircraft before. There's a lot of challenges. So it was very hard, to say the least. And I'm going to show a few images of how we did that. But I want to give a bit of context to the compressed mission. You know, I say 8 days. You know, what would normally be involved in a mission like this? So I've mentioned NASA a few times now. They had 2 planes in the air. They started planning 18 months out. They have a team of 25 people working on this, not full-time for 18 months, but probably half-time. So 18 months, 25 people, half-time, that's a lot of time. The other thing they have is a lot of money. So to this day, even though we're working very closely with them now, I don't know how much their instruments cost. I would hazard a guess and say they had at least $3 million worth of instrumentation over the 2 aircraft, if not per aircraft. So we had 8 days. To start with, we had David and myself. We very quickly recruited outside of that group, but essentially that was, in the end of it, was 7 of us. So it wasn't a very large group. And I did all of the mission planning. David did most of the instrumentation work and the others supported David for a lot of that. Although UQ had their own instrument as well. The other challenge was we had 0 funding to do it. So we actually had to cobble our instruments together with what we had in the lab. Now, that's sort of true. When we got told 3 months out we might be doing something, we did go and buy a couple of extra cameras. But in total, we're talking about $5,000, not 3 million. So it's a very different scale. So this just highlights some of the challenges we faced with this particular mission. So challenging, but super exciting, and we were very keen to go ahead and do this. So I've talked a little bit about planning. Now, what does planning actually mean? So you have to imagine you're in an aircraft flying along. To start off with, you want to be looking out the right side of the aircraft. So you want the aircraft to be flying in the right direction. Now, this thing's coming in at 12 kilometers per second. It's visible for about 40 seconds maximum. That's if you know where to look and you know what you're looking for. Now, what you're looking for is a shooting star, so that bit's okay. Where to look, we didn't know. So we actually had to, I won't say guess, there was some public information out there on the mission overall and what was happening and what was going to do, but you know, we had to be very conservative with our planning to try and maximize our opportunities of seeing it because we had a lot of uncertainty. And the other aspect of that was, you know, dealing with the pilots. You know, it's all well and good for me to draw a line on a map and say that's where we want to go, but it's very important to interface with the pilots and have them working with us. You know, and very subtle things and things that I I mean, as an engineer, I can acknowledge them immediately. It's not something I think about when you're flying an aircraft, but very rarely does an aircraft actually point in the direction it's flying. So due to the winds, it's usually maybe only a few degrees, but the nose is not actually pointing in the direction that you're flying, which means if you're referencing your instruments to the aircraft and you're looking perpendicular out of the window, you're not actually looking exactly where you think you might be. Sounds very minor, but all of these things come together, and that really comes out of these discussions with the pilots. So sitting down with the pilots is very important. Now, for this mission, I keep mentioning compressed timelines. We saw the aircraft for the first time at 6 p.m. on a Friday night. It was also the first time I met the pilots, first time I ever had a chance to speak to them. 6 p.m. on a Friday, what does that mean? Well, at midnight on Saturday, we were flying the mission. So yeah, it was 30 hours beforehand was the first time I met the pilots and the aircraft. So there's a lot of challenges associated with that. But we had a good bunch of guys, RTI, they were very conscious of our needs. And so they selected a crew that were very capable of dealing with sort of things I was throwing at them. So that was fantastic. And this gives a bit of context to what we planned. Now, there's a few things, and I can't see that screen, so I have to look up here for the colors. The black line on the right-hand side is what I planned for the aircraft mission. And that was where we wanted to fly. Over that big red area is the Woomera prohibited area. That's a defense zone where they can lock off the entire zone and no one can enter it, which makes it also suitable for, say, spacecraft coming in that are landing at potentially 12 kilometers per second that you don't want landing on somebody. Now, all going well, these things slow down and they land very gently, but you have to plan for off the area. So that's where they landed the spacecraft. When I say spacecraft, I'm talking about something that's 400 millimeters in diameter. It's not that large, so it's quite small. Now, when you look at that map, you can see in light blue and labeled Hayabusa 2010. That was the re-entry trajectory that Hayabusa 1 took and where it landed in 2010. And this was actually a bit of the basis for all of our planning. Because we didn't have the trajectory of Hayabusa 2, we weren't part of the official observation mission. We could only rely on public information. We knew that the trajectory was slightly further northerly, northwestern direction. So I took a best guess, and that's the dark blue line that you can see. And I said, well, I'm just going to guess it's going to land in about the same area that they're targeting that. It's going to stay over the Woomera prohibited area for as long as possible. So you can sort of see my line cuts across as much of the area as possible there that you can see. And I'm going to do all my planning based off that. Now, as a part of that planning process, it wasn't just based off that line. What you can see, the black line that I planned there for the aircraft track, and those white lines actually show the viewing angles at particular points in time during the re-entry. But if you expand those lines out further, that track covers pretty much all of the Woomera prohibited area. So even if my guess as to where this capsule was coming was completely wrong, we should have had a pretty good chance at seeing it anywhere over the Woomera prohibited area. It did also mean that we weren't necessarily in the optimal position for viewing. You know, there's a bit of a trade-off now. With all that uncertainty, we want to maximize our chances of seeing anything. So, you know, go really conservative in that sense, but we're also a bit further away. We might be very side on, which has actually turned out to be a good thing, but at the time that wasn't necessarily the thinking, and we just hoped for the best, essentially. Now, stepping off sideways, the next part is the instrument design. So I've talked a little bit about cameras, but you know, we're not only going up to video this thing. You know, we're researchers, we need scientific output. And I will even show some scientific results because that's important. That's why we do these things. But it means we can't just take your smartphone, hold it out the window and call it a day, right? Like we have to do a little bit more than that. So there's a bit of construction involved. And what we did was construct things called, well, what I call transmission grading spectrographs. I learned astrophysicists call them something else and I've already forgotten what it was, but they have a different name for them. So we had to build these instruments, calibrate them, align them, and then mount them in the aircraft. I said we only found out 8 days before the mission that we're doing it all. So that's the construct, test, calibrate part. And then the next part is actually mounting them in the aircraft. And I've got a couple more slides about that in a moment. But what this slide shows is the entire array of cameras that we flew. So the left two images are what we called the hyper spectral cameras. So they were from the hypersonics group. So that's my group. And we had 3 spectral cameras on each platform that you can see there. So each of those images represents a window that we were looking out of. and there's 3 spectral cameras and 1 tracking camera. So one of the challenges with these missions is that you actually have to be pointing the camera in the right place. Very important. If you're pointing in the wrong place, you don't measure anything. And yes, it does happen. Probably shouldn't say this too often, but that's what happened to the Japanese observation. They actually looked in the wrong place and they ended up missing it. So, and that's happened to all of us, by the way. That's not special to them. I've done that in the past as well. It's very embarrassing and very annoying, but that's a part of it. That's what happens. So these spectral instruments, they only look at a very small part of the sky. So you've got to be pretty exact with your pointing. So then we also have to have an extra camera called a tracking camera, which gives us a wider field of view. And we know within that field of view where our spectral instrument is. And these are all mounted on tripod heads. So we're sitting there looking at essentially a camera screen and moving this tripod head and pointing the camera in exactly the right place to get the measurements. And there's a lot of challenges associated with that. But that's why the setups look a bit like what they do. The central image I have here is actually the University of Queensland setup, also transmission spectrographs on a slightly different mount. You can see the different style they had there. Second from the right is our astrophysics setup, transmission spectrographs, but with different spectral ranges and resolution. And on the very right is our fancy Sony camera. That's our video camera. We did actually want to get a video as well, and it's just a video to look at because we want to have something to show. The spectral stuff is not visually all that pleasing. So 6 p.m. on a Friday, plane rocks up, Wellcamp, Toowoomba. That's the other nice thing about using private jets is they come to you. That's fantastic. So we actually flew out of Toowoomba. This was all during COVID, so that was actually a really big thing. We had to fly out of Queensland and land in Queensland. So that was actually crucial to being able to do the mission at all. So Wellcamp, luckily, is there. It's big and it worked out quite nicely. We got a hangar there and all that worked out well. One of my favourite parts about this story is actually Lockie. Lachlan Nola is one of our PhD students. He's now our senior PhD student. At the time of this mission, he was about 3 months into his PhD. He had been working with us in the lab as an undergrad student, so we had known him for a bit longer, but he was a very junior PhD student. But Lockie's a good farm boy. He's a really solid farm boy. And what do I mean by that? He's great with tools. He can just build things. He can make anything work. So to me, it was very obvious that for mounting these instruments in the aircraft, that was Lockie's domain. The rest of us are not quite as skilled as him, let's say. We have some abilities, but certainly not to his level. So aircraft rocks up, 6 p.m. Friday night. There's a little bit of toing and froing to meet the pilots. So 7 p.m, I get my team together. I say, right, first things first, we have to mount these instruments in an aircraft. This is a really expensive business jet. They get really upset if you scratch things. They get upset if you break things. They get upset if you do anything to the inside of their aircraft. It gets expensive. So number one priority is do not damage the aircraft. I don't care if the instruments are pointing out the wrong window, just don't damage the aircraft. But we have to make platforms. I want them pointing out the right windows, of course. So Lockie here, just pretending now, obviously Lockie's not here, but Lockie here, very good with his hands. His lead on our platform design, whatever he needs, you guys all do. So Lockie, get on that aircraft, measure up what you need, start constructing these platforms, which he did, and he did a fantastic job. It was only after the mission that he came up to me and he said, look, this was fantastic, amazing, best experience of my life. I really wasn't expecting you to throw all that on me. That scared me a lot. I was lucky to survive the first 30 seconds while you were talking. I was like, oh, okay. Well, you handled it really well. I had full faith in you and fantastic. Everything worked out great. But yeah, he got quite a shock by that. But it was fantastic to watch Lockie. I mean, I was running around like a headless chook doing all sorts of things and I wasn't involved with the platform design, but he was in there bossing our professor around. It was great. Like, first year PhD student, 3 months in, and he's going, David, go over there and do that. You're measuring that wrong, do this. And for him personally as an experience, I think that was amazing. And he really grew out of that. And he developed a lot of his, confidence, certainly. And I won't say construction skills. He already had all of them, but yeah, just his ability to work with the team. And he's really starting to show some of his leadership skills now. And I'd like to think it comes back to that one moment of me scaring the absolute bejesus out of him. So I'll take credit, even though it's maybe not quite fair. But it was a very intense period. The bit that I haven't mentioned yet is I said, Lockie, build these platforms. In 6 hours, we're taking off for our practice flight. because we only had 30 hours until the actual mission, we had to fly a practice flight. It's very, very important. It meant we had to do it that night, which meant we only had 6 hours to construct all the platforms, get the instruments mounted, and get them in the aircraft, aligned and all working. So there was quite a bit of time pressure, as well as do not damage this $80 million aircraft. But as I've mentioned, the boys did a very, very good job. And here you see some of the images of that. So on the left, you can actually see Lockie and David working together. There's no video, so you can't hear it, but Lockie's telling David how it's done. And then David's sort of mounting the platform in the aircraft. So these were aluminium frame construction, wooden platforms, and then there's a foam matting around everything. We just covered everything in foam. No sharp edges, no pointy bits, nothing. Put it in the aircraft, don't damage anything. So that worked out pretty well. They did an amazing job. And that was Lockie, David, and Matt Thompson is in the picture on the right there from UQ. Those guys, really kudos to them for what they put together there. While they were doing that, most of the others were planning the instruments, final construction, alignments, testing. The most photogenic for some reason is Duncan, who's our astrophysicist who was along on the mission. We had a photographer, and for some reason him and Duncan clicked in a visual sense, and so most of the photos are of Duncan. Sure, we'll give Duncan the credit. He loves it. He's actually a very shy person. He hates it when I say that. But he did a really good job. And that was a really good experience as well. Now, Duncan had never done anything like this before. So he's sort of optical diagnostics expert, but he had very little concept of what it means to go in a plane and do this on the move. And so we're talking through a lot of, what you're seeing there is us talking through how it's done and going through that. And the others were doing their instruments. And this was all on the Friday night. I'm going a little bit quicker now because I tend to talk for a long time around this mission. So then we see all the instruments going into the aircraft, mounted there. You can see some of the challenges. You know, the platform's got to be there, but then the instruments have got to be at the right height. Everything's got to fit. The middle image is nice. That's Byron, one of our academics now. You can see the number of laptops there. So one of the biggest problems is actually saving all the data quickly enough onto computers. So the more cameras you have, the more data you have, and you've got to save it somewhere. So Byron was actually running, I think, 5 laptops behind Lockie and myself, who were controlling 2 of the platforms. So that was a lot of fun to set up as well and get all of that coordinated. The final setup and test flight. So you can see everything's going into place there. On the left, you have the 2 guys from UQ. And in the center, you see a bit more of Byron and the discussion there with Lockie and just the general setup of everything. And it gives you a bit of a feel for what it looked like in the aircraft. This is the most comfortable aircraft we've done a mission in. It was big. There was so much space. I'm going to show you photos of the next mission shortly, and you're going to see some contrast there and show you some very unique, different challenges. But that all worked out really well. I mean, I didn't sleep for 4 nights, so I was pretty much on autopilot by this stage, trying to get everything ready, but it worked beautifully, and yeah, I can only say how well it came together. This is another one of my favorite slides, and this is about the nerves. I'm picking on Lockie a fair bit here. So Lockie on the left and the right, quite literally biting his fingernails. So the story here is, you know, we built these platforms with these instruments, but you need someone to point them in the right place during the mission. And we just put Lockie on one of the platforms and said, go for it, you'll be fine. And you can see the headset he's wearing there as well. So we weren't necessarily looking at a screen, but we're actually projecting that into a headset. So he's looking at a screen on his headset and controlling a tripod to point in the right direction there. And in the center, you can see Duncan with a V showing the energy. This is at like 2 a.m. after a couple of nights of no sleep. So he was tanking up on energy. But yeah, we were very nervous flying out. There was so much uncertainty that, you know, would we even see it? Would we be in the right place at the right time? Would we have the instruments pointing in the right direction? Were they sensitive enough? There were so many uncertainties. And in particular for me, luckily, I get to make these presentations, so there's no photos of me being nervous, even though there are certainly a few in the pack. Yeah, I was really struggling on the flight out there. I was just so nervous we wouldn't see anything at all. The money would be wasted. Everyone's time would have been wasted. And yeah, I was petrified, I think it's fair to say. However, things worked out okay, which is always nice. So on the left, this is a photo actually taken during the mission. And I don't have a suitable laser pointer given we've got people in Zoom and things like that. But on the photo on the left computer screen, you can actually see a line across the center of the monitor. That's actually a live measurement of the capsule. So this photo was captured while we're measuring the capsule. And it was either from mine or Lockheed's instrument, but I'll say it was mine because, yeah, definitely mine. So we've got the live measurement there. And 60 seconds later, after we saw it, and I'm going to show a video in a second, so it's fine. We saw it. The relief was just immense. By far, the biggest relief of my life was that actually worked out. You can see in the center photo, everyone being excited. And on the right is myself and Alan Payne, who actually sponsored the mission from RTI. Oh, that's interesting. Software update. Make that go away. And I think you can just see how relieved I am. Alan was never really concerned. He's a very relaxed guy. He's happy with whatever. I was very concerned because I thought the relationship with him was very important going forward. So I was relieved. He was just happy. Right. So I've talked a lot about this. What is it? So this is a video. It'll start playing in just a sec. What you can see at the moment is just the star background. The audio should play as well. You're going to hear a few things. I'm not going to talk over the audio, but you'll see it moving around a bit and you'll just see stars. You're going to hear the pilots talking through the intercom. So it's really unfair. The pilots have these massive windows and they can just see the entire sky. They won't share those windows with us for some reason. So we've only got these tiny little windows and we put instruments in front of them so we couldn't even see out of the sky. So we couldn't see it at all. I've never seen one of these things live. It's very disappointing. So you'll hear the pilots telling him where to look. What you will hear is a couple of people saying, oh, look, there it is. That's cool. So there was one free window and we had a couple of guests like Alan with us who saw it. And then at the end, you're going to hear something funny and I'll explain that.
In view, just to 45 to the right.
To the right.
And the pilots.
See it.
Up about 20 degrees.
Yep. There. Static lights in the light.
In view, guys.
A big light coming straight across. See it?
Good work. Sorry, missed it. Okay, can't see it.
So that voice is David Buttsworth. And he hates it when I play this video with audio in public. The sorry missed it is very funny for us. Like, he took that video. It's an awesome video of this massive shooting star. You know, this is a 400mm object at about 200 kilometers distance, moving at 10 kilometers per second across the sky. And he's got this great video, and that's the video we show everywhere, right? There's this audio, sorry, missed it. Now, the reason for that is his objective was actually to be the first person to spot it. So the idea was he had a very sensitive camera. He should, like, from a pure sensitivity point of view, he should have been the first person to see it because we didn't know where we were looking and you saw him sort of jumping around looking for it. He didn't get it first, and that, well, he was the first camera on it, but he wasn't the first person to see it. So he was really disappointed himself that he didn't see it first, hence the sorry missed it. But realistically, great video. We're all happy, so that was fantastic. So that's what all the excitement was about, was that one big shooting star. So we saw it for about 26 seconds, that video. It was visible for about 40. I mentioned that before, and you heard the pilot saying they could see it earlier. We just didn't know where to look. In future, that's going to be different because after our recent successes, we're actually now included in the official mission. So we'll have trajectory information. So that'll be very nice. And I do have to bore you with a little bit of science. It's important. This is why we do it. It's my only slide of science that I actually show in this talk. So that's positive at least. But what we have here are spectra. This is the science that we're going up for. So on the left, in the bottom of the left, what you see is wavelength on the x-axis and intensity on the y-axis. You can see it sort of goes up in a bump and there's a bunch of lines going up and down. Now, those lines going up and down, they represent oxygen atoms, nitrogen atoms, and there's even a hydrogen in there. So that's the radiation of the gas in front of the capsule. From that, now there's a lot of work that goes into this, but from that measurement, we can determine how hot the gas is and how much of that temperature is going into the capsule, and a lot of the chemistry. I said before, there's large uncertainties. We can provide data to help with those modeling from that. The big shape that you see, the big bump, that's something called black body radiation. That's the actual capsule itself radiating. When things get hot, they glow. This is this an extreme. So this is the capsule glowing at close to 3000 degrees. And on the right-hand side, I'm not going to go through it fully, but that's the process of where we take the raw image of the spectra, we turn it into a line spectra, and then we can fit a black body curve to it, and that gives us the temperature. Memory serves 2920 Kelvin, this particular image. So we actually know how hot the surface of that capsule was in time from our measurements. And that's really valuable information to feed back to designers. And that actually helps change future designs. Now, we weren't part of the official mission, so our data hasn't been incorporated yet. NASA went up, they got great data as well, very different to our data. Different in the sense they were looking from somewhere else, not in that our data was completely wrong. They correspond quite nicely, but it was from a very different angle. The NASA data from this mission has actually changed the next Mars capsule design. So there's a Mars mission launching in the near future, and the Hayabusa 2 data changed the design of the capsule on that mission. Quite significantly, by the way, about 30% on the thermal heat shield weight. So that gives a bit of an indication of what our data can do. So that's why we do this, and that's the exciting stuff. So that's the capsule. Now, it's Astronomy and Science Week, so I do have to show a meteor shower. Conveniently, our other mission was also a meteor shower, so that works out really well. This was a mission, well, a meteor shower called the Tau Hercules meteor shower. I presented that Hayabusa mission, essentially those slides, to our astrophysics group. We had Duncan on the mission, they already knew about it. So I said, do you guys want to see what we actually did? This is not really related to astrophysics, but there's certainly overlap in some of the parts and definitely interest. So first half of the presentation tonight, I presented, and someone by the name of Jonty Horner, sitting right here, said, hey, you know what? There's other stuff you can look at as well. I did ask for other things to look at, and he said, there's this Tau Hercules meteor shower that's coming up. This was sort of November last year, I think we had this discussion. May next year, Tau Hercules meteor shower. And there's a few really weird things going on with it. There's radar data, telescope data, but there's some modeling that's been done and there's some uncertainties around it. Like, this is a really unique event, or it could be. And this was actually the catch. So he mentioned the modeling by someone called Jeremy Vabayon, who I mentioned earlier, leader in the world for doing the dynamics modeling of meteors and meteor showers and predicting them and how strong they'll be. And the only way he could get his models to match what they had seen in telescopes of this particular meteor shower as it's traveling around in space was by making an assumption that had never been seen before. And it was to do with a breakup event that happened in 1995. So there's a comet called the Schwarzmann-Wachmann comet, or 73P if you want to keep it simple. And there was a certain breakup event that happened in 1995, or was discovered then. And that caused part of the comet to break up and send out dust ahead of the comet. I think it was ahead. Yeah, well, it would have been ahead. But for it to match the data, or sorry, to match the modeling, for the modeling to match the data, there was an assumption that the speed that it ejected at was significantly higher than what had ever been seen before. So normally they would have expected it to be a slower ejection speed, and that would mean that this particular part of the Tau Hercules meteor shower would not intersect with the Earth's atmosphere. But Jeremy's modeling, based to match what was in the radar telescope data, had to say that it was faster than what had ever been seen before, which means it would intersect with the Earth's atmosphere and there would be a meteor shower. Now, when I say meteor shower, be a little bit careful here. Tau Hercules describes essentially a whole suite of meteor showers. There's quite a few of them that all belong to the Tau Hercules family, and I'm referring to one very specific part of that. So would we see it at all? Don't know. Only if his new modeling is correct, which is assuming something that had never been seen before. So that was really interesting. Now, the other interesting aspect of that is that I actually knew Jeremy from my time working in Europe. We'd done an airborne observation before. So when I said to Jonty, oh, Jeremy, yeah, okay, I'll give him a call and ask. I'm very proud to say Jonty was a bit awestruck, and that's very rare with Jonty. So that was nice to surprise him like that. And it turned out that my former boss actually happened to be spending a couple of weeks in Jeremy's lab at that time. So I called him up that night and just said, hey, you were Jeremy? Sweet. Can we just talk about this Tau Hercules meteor shower? Is it worth going up and doing this observation? And Jeremy was super excited. He's like, yeah, this would be amazing. Like, if we see this, we could prove that the theory is right and completely new, like hasn't been seen before. Can we make this happen? And that started this journey. So Jonty actually started the journey. And there was many steps along the journey. And We were really hopeful actually to get 2 planes for a number of scientific reasons, which would have meant that we could have taken Jonty. And I still feel bad about the fact that Jonty didn't get to come on our airborne observation. And I know it still hurts him because he told me that only about an hour ago. But there'll be another opportunity. So we set this up, but this was a very different beast, and it also involved very different people, and I named them all at the start. So I'm going to talk a little bit about them and their instruments as we go through. Now, planning this mission was a new challenge for me. Now, there's a few different things for me. I'd never done a meteor shower before, so conceptually, there was a few things that were quite different. Now, when you do a capsule, you have to look somewhere very specific, and if you miss it, you're in trouble. The nice thing about a meteor shower is it's everywhere. So if you've got a camera and you can point it at the window, you're pretty much going to see something. That actually creates its own challenges though, because you want to cover as much of the sky as you can and get all those different types of measurements that you want. Now, for this one, we had an international team, and this relates a bit to what we're trying to set up within our group and within our capability. And that's not just that me and a couple of my mates get to go up in an aircraft every now and again and have a lot of fun, but we want to be an internationally recognized group that works with international experts, getting real data out that's important to the community. So for this mission, we actually ended up reaching out to Jeremy and his team in Paris, Stefan and his team in Stuttgart, and Juraj and his team in Slovakia. Now, they are leading experts in meteor observation, spectroscopic. Jeremy from a modeling side, but he's also done these sorts of missions before. Juraj does spectroscopic measurements of meteors fairly regularly. And Stefan's expertise is actually they recreate shooting stars in the lab. So they have a plasma wind tunnel and they take spectra of meteors in the lab regularly. And that's a project that I've been involved in the past as well. So it was an international team across, well, two time zones, sort of 3 if you count America. And there's a funny story behind that I'll get to. So I had to try and coordinate 4 different countries, 5 if you count where we were doing it. So I haven't actually mentioned that yet though. The best place to observe this meteor shower was actually in the US. So we had to fly the mission in America. It was not worth seeing elsewhere. You could sort of see snippets of it somewhere else, but not the level of detail we needed for what we were trying to do. So we had to coordinate all of the instruments. We had to coordinate an aircraft. We had to coordinate mounting them. I've mentioned before that it gets really expensive if you damage aircraft and you shouldn't do it. It gets even more expensive when you're using a commercial aircraft in a different country that's not from a company you're affiliated with. So we had to be even more careful over there. We didn't have the time to build platforms over there, so we had to do all of that here. We had to be sure that we could integrate all of the instruments from our collaborators. We then had to get to America post-COVID, so it was somewhat easier, but there was still some challenges there. We then had to integrate all the instruments into the aircraft. I mentioned before about pilots, same story here. We had to work with these pilots for what we wanted to do, and we had to do all of that in 2 days this time. Now, planning we had a bit longer, so that was okay, but we received the aircraft once again in the order of 36 hours before the mission. There's a bit of a theme here. I'm hoping to buck that trend one day, and I'll mention another mission shortly where maybe that will actually happen. So more challenges again, very different type of mission. So flight path planning, very, very different beast for me. It's not so much about being somewhere where you can be in exactly the right spot at the right time to see what you want to. In this case, light pollution is actually the biggest problem. So what you're seeing here is a map of the southern US. On the right-hand side, the big white dot is Dallas, and that was where we flew the mission from. The color that you're seeing there is actually light pollution. So the big white dot is because Dallas is a big city and there's a lot of light. So to do this observation, we want to avoid light as much as possible. So we planned the mission path that you can see in dark blue there, starting from Dallas and moving out to the west. Now, the other aspect we had to take into account here is you can see all the yellow pins there. They're actually ground stations that were observing this meteor shower from the ground. The reason it's important that we fly through them, as you can see there, and why we planned the mission this way is that if you can get measurements of individual meteors from 2 different locations, you can do some really fancy astrophysical triangulation. Well, the triangulation is not so much the astrophysical part, but you can back out the orbital mechanics. And that's one of the important scientific outcomes. But to do that, you have to be within 60 to 100 kilometers of each other to get the right sort of measurements for backing out the orbits. Don't ask me why, that's just what the experts tell me. So I had to plan the mission to try and go as closely as possible through those yellow dots to be within sort of the 60 to 100 kilometre away range and getting those measurements. So a bit of a different planning challenge there, but that all worked out pretty well. So what did the aircraft integration look like? So I mentioned a little bit before about we had to set a lot of this up here before flying out there. So one thing we were lucky about is we actually knew what sort of aircraft we were getting this time. So we had a Phenom 300. I did mention during Hayabusa that this is somewhat smaller than the Falcon 900 that we had for Hayabusa. It is. It's significantly smaller. So there were some challenges around that. But one of the good things about that is that within our larger group of partners here in Australia, our charter company actually has a Phenom 300. So we're actually able to fly a test flight with the platforms and at least our instruments on a Phenom 300 in Australia, so that we could get all the platforms built here, and we actually took them with us to the US so that our collaborators could then essentially just plonk their cameras on. So we got a lot of that work done here. And so the 2 days there was all about integrating that into the aircraft there. It was hot. You can see us having lunch there. So there was some interesting challenges about summer in Dallas. It was about 36 degrees on the tarmac, which was unpleasant. We did have the aircraft hooked up to air conditioning for a while. Turns out if you run that for 8 hours during the day in 36-degree heat, even though the pilots thought it would be fine, you end up cooking the aircon. So that stopped working after the first day. Its own problem. So the second day was less fun. But we got there. So we hung out under the wing when we had to have a break, because as you can imagine, inside the cabin was even hotter. What you see there are some of the instruments that we flew, and they look a little bit different to what we had on Hayabusa. Some similarities, but quite a bit of difference. One of the reasons for that difference is we're targeting very different things. So, you know, Hayabusa, we were really looking for spectral information. We wanted that radiation information. For this mission, actually, simply seeing meteors, as many as we can, and counting them is probably the #1 outcome. It sounds really trivial, but it's actually really important. And I mentioned much earlier in the talk, you know, the speeds at which these things were coming in. Tau Hercules is a really, really slow meteor shower at 12 kilometers per second, which means they're really faint, which is one of the advantages going up in the air, because that helps us see them. But it also means we need to maximize our sensitivity on the instruments. So we're really keen to get up and just see as many as we could. But also have some spectral instruments. And what you see there is, again, cramped setup. Hopefully on the next slide, we'll see just how cramped it was. That shows some of the configurations. You can see the black cloths we've got over, try and minimize light pollution, and all the setups that we were putting in place there. So that was very interesting as well. Let's see on the next slide. Yes. So there's the aircraft. So talking a little bit about the mission now. So on the left, you see the team in front of the aircraft. We didn't have a photographer this time, so the quality of the photos are somewhat less. Apologies for that, but at least you get a bit of an indication. I quite like that central image. It shows the instruments sort of pointing out of the window and what we're looking at there, trying to get all of our angles covered. And on the right, you see how cramped it was in there. So you can see how we're sitting there. You have to imagine we've got about, I think it was 9 laptops, as well as all the instruments that we're trying to squeeze around. You can't see them there properly, but I'm on the front right there, and I'm actually leaned forward because there's an instrument directly behind me, and I couldn't lean back at all. Otherwise, I would have been knocking the instrument, and it was very cramped. We couldn't move. The meteor shower, the measurements went for about 3.5 hours, and we couldn't move around the aircraft in that time. So we were locked into our, I'll call them seats, although I was mostly on the floor. Other guys were right on the edge of the seat. Some very interesting challenges. That was all the setup. But of course, you're probably actually more interested in what we got to see. So this first video is going to be very clear. This is one of the more spectacular meteors that we saw. I'll try and play the video a couple of times. One of the things I'll point out first of all, there's actually 2 meteors in this video. So watch carefully. So I think the one meteor was very, very obvious, I hope, and very spectacular and very exciting. And, you know, the fact that we got things that look like that for us was just amazing, because it looked very cool. I'm just going to go see if this works. Oh, come back onto it. I haven't actually seen it on this screen. So I want you to look just to the right of the really bright meteor while it's coming in and see if you... Can I see the second meteor? Yeah. So that second one is actually what most of them look like. I like showing that really bright, fancy meteor, the spectacular one. Sadly, of all the meteors we saw, probably less than 1% actually look like. Most of them look like the other one. But scientifically very relevant, right? Like I don't want to underplay it. Very important, but they're not all spectacular. So this is an interesting collage that I put up. I like showing this. Each one of these images represents 5 minutes with from one particular camera. So each of these images is a stack of 7,500 individual images over a 5-minute period. And you can see quite a few different phenomena in the sky there. So they've all been aligned reasonably well. All of the streaks that are going straight down-ish are the Tau Hercules meteor shower. Now you see a few other things. You can see satellites going across the sky. I don't think in these images, sometimes you see a stray meteor, like there are still random meteors that are not related to the meteor shower. They go off at different angles. So there's a lot of different stuff going on here. But you can see the number of meteors, the Tau Hercules meteors that we saw in even a 5-minute period in each of those images from one camera. We had, don't know off the top of my head, roughly 15 cameras pointing out of the aircraft on both sides. So, you know, we saw a lot of meteors, which was super exciting. As we were flying up to start the mission, we said, if we see one meteor, we'll consider this mission a success. Luckily, we saw a lot more than that, as this proves. Talked a little bit about spectra earlier, so I'm just quickly going to show some of the results from the collaborators here. So IRS is the University of Stuttgart, the Institute for Space Systems. So what we're looking at here are spectral results. So on the left, we've got 2 still images. Now, top left image is probably the easiest to explain what's going on. You can see 2 bits of color there. On the very left, there's sort of the green going into purple streak. That's actually a star. So that's the spectrum of a star. And above and to the right of that, it's a bit messier, but you see something similar, but it's sort of smeared vertically. And that's actually the meteor. So this is a single frame out of a video as the meteor is moving down. And the image on the right, well, it's actually a video that I'll play now, and you'll see that a bit. In the still at the moment, you can see quite a few of the stars, the spectra there. And when I play the video, we'll see as the meteor comes in and see the spectra of the meteor. Do that like this. Watching it, right? Everyone see that? So I'll just show it with a mouse here. Hopefully everyone in Zoom world can see it as well. But in this area here, I'll play it again now. There's going to be... Now, if I can pause that appropriately. There we go, perfect timing. So this is paused halfway through. And you can see it's not a continuous line of color. You can only really see a couple of streaks of color there. In particular, a red and a green one. These actually tell you a particular element. One will be sodium. And I don't even know off the top of my head, potentially potassium. Probably, yeah, looking at Jonty, he's a bit more of the astrophysics. So sodium and potassium, I'll say as a guess, I'm very sure on the sodium, not so sure about the other one, but we can see those lines there and they tell us what the meteor is made of. So there's actually more information embedded in there that's a bit hard to pull out in a video like this. And when we do the analysis properly, we can actually pull out what's burning up. Sodium, potassium, there's going to be iron, definitely, carbon elements. So the reason we do the spectra is to get an understanding of what this thing is made of. What's the comet made of? This actually gives us insight to the inside of a comet. And it's a relatively fresh breakup being from 1995. These 2 images are very similar, and these are images. These are from our Comenius University, from Bratislava colleagues. Very similar thing, just not in color. So these spectra again. So if we look at the left image, on the right-hand side of the left image, you see a bit of a streak. That's a single frame, and that's the meteor moving through the frame. And off to the left, you see the spectra. And once again, you see a couple of the bright lines there, but you also see that there is a bit more information there across in the horizontal direction. That's the wavelength direction, and that's the other information and species that we're interested in. The image on the right is actually the full video stack into a single image of that particular meteor. So that's why it's streaking down. So it's actually 4 or 5 frames over a fraction of a second. And that gives us, from that, it's a little hard to see, but on the right-hand image, the very left line, you can see it actually starts dim, it gets really bright and then goes dim again. So that actually tells us, assuming that's the sodium line, that early on in the burn up, there's very little sodium. And as the meteor actually reached its core, there's a lot more sodium in there. So that's burning up. That's why it's getting brighter. And then as it burns away, it dims off again. And from that, we can actually infer things from like how long has that bit of dust been exposed to sunlight? How long since the breakup? You know, the outer crust has actually been essentially evaporated away over time from sunlight, but the inside is untouched. And all of the different dust particles can react differently, and we can glean different bits of information from that. That's a bit of an insight to those two setups there and the sort of information we can get out of that. Now this one here, as you can feel, goes especially dark. This is a video from our Paris colleagues, from Jeremy. This is a very special video, and there's elements to this, and I'm going to talk a little bit through it before I show the video. In this video, they detected something called a meteor cluster. So there's actually going to be 34 meteors in 6 seconds. This was caught very, very late on in the mission, so it was a bit of a surprise to catch it. The significance of this is from a meteor shower. You know, you see images of meteor showers, you see meteors everywhere. You saw my composite images, right? They were taken over 5 minutes. To see 34 meteors in 6 seconds has only ever been recorded once before in the history of science. A meteor cluster, there has been 6 recorded in total, including the one I'm about to show you. The other 4 were 4 meteors or less in total. So to capture 34 in 6 seconds is really a phenomenal outcome. It's hard to call an achievement because in a sense it's luck, but as an outcome for a mission, it's amazing. Now, this is another one where the video doesn't play automatically. Let me run over here and play it for you. This is going to loop, so it's going to run for a lot longer than 6 seconds. But you can imagine in 6 seconds, you'll see them, and you're going to see a lot of these little dots. So you can see these are the weak meteors. The reason it's so dark in the room now is so you can see it at all. But there's actually 34 of them in 6 seconds. And this is really scientifically by far the best outcome of the mission. There will be there's plenty of them, but this is really significant. So we're just super excited to have been involved with this and to be able to do that. So from my point of view, I mean, I've said it many times, I'm not an astrophysicist, I'm not a meteor scientist. My excitement comes from the excitement of my astrophysics colleagues. And this is just an amazing outcome. And for me personally, to have been able to provide them the opportunity to capture this and to be involved with that is just amazing. And that's what we want to do going forward as well. Like that's just, you still get a tingle in your stomach, I think, when you get an understanding of how significant these outcomes are. Just fantastic. So just about bang on time, which is amazing. It's very handy having a clock. And I'm just going to finally say thanks to the team. And this is everyone in the team. These 2 photos are from the Hayabusa mission because they're the nice ones from our professional photographer. But everyone that's been involved across the board, Hayabusa, the Tau Hercules mission, all of our European colleagues, Cam, who's not in the photo, but he's in the audience, and he'll be happy to answer questions about how annoying I am with IT questions. Yeah, I mean, and Alan in particular, I really just have to say thanks to him to make all of this possible for the scientific outcomes. So thank you very much for listening to my story of my 2 missions, and I'll be really happy to take any questions that you might have.
Awesome. Well, thank you very, very much for that. I'll just bring the lights up so that we can actually see the questions, and I'll see if there are any questions.
Do you have to take the aircraft windows into account? Because you'll be filtering out frequencies that you may be interested in, they may not be in the visible spectrum, you may be attenuating frequencies along the way?
Yeah, absolutely. Absolutely crucial. So for these 2 missions, we're really limited by our windows. And that's, yeah, it's a big problem depending on what we're looking for. So we can glean huge amounts of information out of the visible and near IR where the windows are transmission or where there is transmission. But so what I haven't mentioned, I was going to mention, is we have another mission next year. So I've mentioned the NASA collaboration. They have a capsule coming in September next year, and they've actually invited us to be a part of their mission. Now they have specialized aircraft where they can swap out the windows, and they've offered us a seat on one of their aircraft as well as asking us to bring our own aircraft. And we're actually going to field a UV ultraviolet instrument on their aircraft where we can swap out the window and get down to probably about 250 nanometers.
Is the speed of the aircraft critical, or is it merely being able to get to the altitude?
Yeah, it's all about the altitude. The speed of the aircraft's no longer relevant because we're so slow compared to the actual object. And the
I
reason,
think I have a solution for your window problem.
very interested. The reason we go up in an aircraft is actually to avoid atmospheric absorption. The lower you go, the denser the atmosphere is. So the lowest 10 kilometers of the atmosphere are the densest, and that's where we lose most of our signal. So being able to go above that means we avoid that issue. And there's also, as Jonty knows, because he's worried about it at the moment, these pesky things called clouds. So when you're on the ground, if they happen, there's not much you can do about it. So being in an aircraft, you can just fly over the top of them and ignore them. And that actually happened for Hayabusa too. So that was very beneficial.
You spoke earlier on about moving at 12 kilometers per second, things get hot about 20,000 degrees, and there was a variation of about 50% there. Can you give some perspective on the difference between, I'm assuming, what is 10,000 degrees and 20,000 degrees in terms of something that I can sort of resonate with? Like 20,000 degrees is very hot. 10,000 degrees is very hot, but what's the difference between those two? Some sort of perspective, thank you.
Yeah, so the uncertainty is really more in the radiation. So it's how that, so the gas is at 20,000 degrees and it transfers some of that heat to the capsule, but certainly not the whole thing. And the amount that gets transferred is where there's about that 50% uncertainty. What that really means is that really dictates how hot your capsule will get and how much thermal protection you need on the front of it. So on a capsule entry at 12 kilometers per second, essentially the front of your aircraft burns away. Now, the amount that burns away is dependent on the amount of energy that gets absorbed by it. And that's essentially doubled by doubling the temperature, not quite. In fact, if you're just looking at radiation, it's more, but there's other effects as well. So it really is essentially a factor of two. So you have to have a much higher safety margin on your thermal protection system with that uncertainty, but it's not the 20,000 to 10,000 in terms of the surface temperature, but it is the double amount of energy that comes in.
First of all, thank you for the talk. That was very interesting. I was interested in one of the last slides you showed about the meteor shower, the 34 that happened over a short period of time. The period at which the light was seen seemed to be the same, but very similar for each individual meteor. And I was wondering why is that the case? Is it because the particles are pretty much the same size, or they decelerate at the same rate and the light goes out because they slow down?
Yeah, same size is an element of it, although probably not so much. So you would have noticed there's a big difference in the brightness between them, and that's really related to the size. The reason they're going for the same amount of time is the only way you can get a meteor cluster is if an object breaks up very shortly before entering the Earth's atmosphere. I say entering the atmosphere, we actually entered the stream, but that's a different matter. And that means all of those particles actually came from one single element. So when it broke apart, and so they're made of the same particles, they're traveling at the same speed, they're entering at the same angle, but they would be slightly different sizes, and that's where the slight differences do come from. But they're essentially very, very similar due to that very recent breakup, sub-breakup, I'll call it, of that element. Yeah.
Just as the microphone comes down, I actually saw a meteor cluster when I was about 14, 15 years old, along with members of the Astronomy Society, of which I'm now president back in the UK, from the Perseid meteor shower, and we got 7 in about 4 seconds. And 'cause normally when you see a meteor, when you see a shooting star in the sky, you go, oh, wow, look at that. And by the time people turn around, it's gone. And I said, oh, wow, look at that. And everybody turned around, and then there was another, and then another, and then another, all following the same path. And it was the same thing, something had just broken up. But I didn't realize how incredibly rare that is in terms of reported event. Obviously, we didn't report it because it's just we were watching the meteor shower and people were relaxing. I think a couple of the people thought it might have been the result of the drinks they were having. Anyway, sorry, that was just an aside.
Yeah, thanks for the opportunity. Outside influences like Starlink, is that going to make your job worse, or you can account for it?
It depends on the mission objectives, is the short answer. So something like a spacecraft capsule, no effect at all. They're so much brighter than the background, essentially, that it won't matter at all. It's more in the astronomy field. And so meteor showers, for example, where there might be some interference. For the work that we're doing, it's probably quite minimal because, you know, even if you imagine Starlink going across there, it goes over in maybe a minute, and we might miss a few of the meteors in a meteor shower. It's probably more people like Jonty and their guys where they're looking at deep space where they have bigger light pollution issues yeah, for our work, specifically what I do, it's not such a big deal, but I know it is a big deal in other fields.
Well, there's a couple of things I'd add to that. In terms of the meteor shower stuff, it won't really interfere with the view of the meteors because the meteors are moving quicker than the Starlink satellites across the sky. What it could hinder, though, is limiting our ability to find the objects that are the parents of the meteor showers, the comets and the asteroids, that also pose an impact threat to the Earth. Now, that's relevant from the meteor shower point of view because someone like Jeremy Vaubion does his modeling based on the knowledge of the object that's going around the sun that is shedding the dust. If we don't know the object's there, we can't predict the future meteor outbursts like this. So I can definitely see an impact there. There's also an impact the other way around, which is the work that's been done on predicting these meteor outbursts. And the most famous of them, of course, were the Leonid meteor showers more than 20 years ago, is of importance exactly to people like the people who run the Starlink satellites, because when you get a really big outburst, not like the Tau Hercules, but bigger, that is stuff coming in that can hit and disable satellites. And the greater the density of material coming in, the greater the risk. And this is a real concern. And you've got this unusual feedback that the more things we put up in the sky, the harder it will be to find the objects that can produce the outbursts that will get rid of the things that are in the sky by destroying them. And so you've got a really odd resonance there. And the Starlink satellites are going to be something of a problem from that point of view because they'll make it harder to see objects that could pose a threat, but could also leave behind debris trails that would pose a threat for the satellites. So it's a really interesting situation. It's a great question. I'll just hand over to Des for an online question.
Yeah, that's a nice segue into a question Gwyneth asked right back near the start of your talk, and I think she thought I'd missed it, but she would like to know how much space junk is estimated to be in the Earth's gravitational field. Tricky question. That
is a tricky question.
String, isn't it?
A vast amount. Tens of millions of pieces of space junk of varying size is the key element there. You know, space junk varies from millimeter-sized pieces that are left over from a collision, for example, up to defunct satellites, and potentially the ISS in the future, although that's being redebated again. You know, so there's a wide range of what can be classified as space junk. There's also rocket components being the very topical one with the SpaceX components that landed in New South Wales. So yeah, I mean, tens of millions of individual pieces.
You said earlier about the 30% change for the Mars rover from the science from HiBoost. Was that a 30% increase or decrease to shielding?
Yeah, I don't actually know, to be honest. Sorry, Cam. I know you're disappointed in me. No, yeah, I don't actually know. I would assume it's a decrease because they tend to go very, very conservative on missions like this. But I'm not 100% sure.
Hi, great talk. I loved the pictures. They were very fun. I was just wondering, you mentioned that NASA is now working with you and you had a look at some of NASA's the pictures and like scientific things they got from the Hayabusa 2. Did you ever show NASA your scientific findings, and did they have any reactions, or did that have any impact on what they're doing now?
Yeah, absolutely. So we were actually invited to present all of our data alongside NASA at a special session in a conference. So we were over in the US doing that recently. So they were very excited to see that all. And this wasn't by plan, but it turns out our data is actually really useful for NASA from this particular mission even. And going forward, it's actually changed the way they're going to plan these missions. So, you know, when I showed the map of where we flew compared to the re-entry, you know, we were pretty much side on. So we were looking across the re-entry. There's advantages and disadvantages. And the biggest disadvantage is that you can only see half of the spacecraft at most, right? Because the other half is around the back of what you're looking at. So both of NASA's planes were essentially downrange. So they were looking straight back at it and it was coming straight at both of their aircraft, which means they got really nice data. They saw it for a lot longer. They also knew where to look, so they were able to find it really easily. But it turns out they missed a lot of data as well by doing that, by having that other angle. So they saw our data and went, you know, that's really complementary. Going forward, we actually need to think about this more and have those sorts of angles as well. So there's been direct feedback in that regard. And as I mentioned, they've invited us to come along and play with them in the future, which is super exciting.
Just to finish up, one question I'd have, and this may be stretching your relationship with RTI maybe a bit too thin, but there's a history of airborne observatories. The most famous is the Kuiper Airborne Observatory, and there's another one that's more recent whose name has totally eluded me, even though I've had data from it before. And basically they're giant commercial aircraft where they've chopped a bit out of the side and they get up there and then they open the door and stick the telescope out. And it's a little bit more convoluted than that. But is there any possibility in the future of you persuading RTI to let you turn one of their planes into a convertible for these kind of observations?
Are you talking about the Sophia aircraft? Yes, so I know the Sophia aircraft quite well, actually, because it's University of Stuttgart, where I did my postdoc. We're involved with it, and it's actually just flown its last mission. It's been retired as of last week. So what John Dee's talking about, Sophia aircraft is a 747 aircraft, which had a 3 by 3 meter door put into the side of it, sliding door. And they actually go up in the air, get up to altitude, and they've got a 3 meter telescope in it, I think, 3 meter, yeah. So while they're flying, they open the door and take measurements out of it, which is great for astrophysics. I did suggest that RTI should buy the Sophia aircraft. They were not that enthusiastic at owning a 747, sadly. So yeah, pretty unlikely, I'm afraid, in that sense. Interestingly, we are interested in modifying a commercial business jet that would operate commercially normally, but then be modified for our purposes. And one of the things we're talking about is pod-mounted cameras, which might also open opportunities like that up for astrophysics for very specific events.
We do have an online question.
It's a little bit different topic again. Perhaps it may be Jonty may need to tackle this one again as well. What elements make up the dust on the moon?
Jonty question.
That might be a me question. So basically everything that kind of makes up the Earth as well. We've got, in a really broad sense, the solar system is all made of the same kind of stuff. So if you look at the sun and measure what the sun is made of, that tells you in broad brushstrokes what everything else is made of. You then have a factor that is what it can hold on to. So obviously we don't have very much hydrogen and helium on the Earth because our gravity is not strong enough to hold on to it. So you get a component from the sun tells you everything that was in the pot, and then gravity plays a role. For the moon and the Earth, you then get an extra complexity in that they were once one single object that was smashed apart in a giant collision. So we know that the bulk composition of the moon is not identical to the whole of the Earth, but rather very similar to the Earth's mantle and the crust, which were the bits that were splashed off in the big collision, which means it's rich in the things that float to the surface on the Earth and somewhat depleted in the things that sink to the core. So the Earth has more iron and nickel than the moon does, but the moon will proportionally have more aluminium and silicon and things like that. The dust that's on the surface then is very much like if you imagine the surface layer of the Earth, in a broad sense, being mashed up and smashed up by impacts and ground down. So the dust grains themselves are incredibly fine and incredibly sharp because you don't have an atmosphere to weather them down. You've got these incredibly abrasive, unpleasant bits of dust. But they are essentially rock, like the rock you find on Earth. And those rocks will vary across the surface of the moon. You've got the mare, which are the seas on the moon, which are mainly flood basalts. They're places where lava has poured out essentially from the interior of the moon as a result of big impacts and made big flat layers of lava. The hills on the moon are made of different stuff, but it's all essentially rock, a bit like the Earth. So that's kind of a broad brushstroke thing. Should note, I'm not an expert in lunar rocks, so if you wanted a real answer on that, you could talk to people. And we do have some people in Australia who have handled the rocks that were brought back by the Apollo astronauts and have taken them into their lab and worked with them. One of them actually works down at UQ. And again, I'm having a senior moment at the minute and really struggling to remember his name. But we've got world experts here in Australia who actually work with the rocks that the Apollo astronauts brought back and have fired lasers at them in labs to experiment with them and figure out what's in them. So there are people who could give you a much better answer than I did there. One more question at the back.
Do all countries work together quite well with this? Like, are there issues with like Russia or China or anything like that? Or
depends on which aspect you're talking about. Meteor shower type work, the pure scientific work, yeah, generally we do. Now, we don't have any direct collaborations with many countries, but the scientific community, and you see it with the ISS actually at the moment still, it tends to try and avoid the political complications.
I'll ask you all to thank Fabian again for a fabulous, fabulous talk. And that really brings to end the formal part of tonight. I would encourage those of you who have further questions to come down and have a chat, be friendly. And thank you very much for coming along and keeping us company tonight. Thank you.